in this lesson, we are going to look at taking the derivative of inverse functions, which will lead us specifically to the derivative of inverse trig functions eventually. I am going to record this lesson in a series of videos because I do have a lot I want to share with you, and I don't want you to get overwhelmed by one really long video. Plus, it takes way too long to format one really long video. So let's just start with the basics about inverse functions. Okay, so if I asked you what is the inverse? What is the inverse of f of x equals x squared? Okay, so inverse in math is like what sort of function can I use to undo this function? Okay, or they're opposites of each other. Now, technically, functions only have inverses if they are what you call 1-to-1, which means for every x you plug in, you only get out one y, and for every y you plug in, for every y you get, you can only plug in one x to get it. I know that's kind of weird the way I said it, but graphically, a function only has an inverse if you can switch every x and y and it is still a function. But if you did that with x squared, if you switched every single x and y, you would get a sideways parabola like this, and that's actually not a function. So x squared only has an inverse when you look at half of it at a time. Okay, I know that's supposed to go through the vertex. So I specifically want to know what is the inverse of f of x for just the x's greater than or equal to 0. Okay, and maybe you can look at this sideways parabola, and if you were to put it on a coordinate plane, it would actually look like this. And if I only looked at the x's greater than or equal to 0, I'd be looking at this half of the graph, and perhaps you can tell that that's the square root of x. Okay, and so the inverse of x squared is the square root of x. But mathematically, how do you find an inverse? Okay, so let's go back to Algebra 2 for a minute, and let's remember how to find an inverse. Okay, so you start with your function in terms of x's and y's only. Okay, then you switch the x and the y, and then you solve for y again. So that would require us to take the square root. Now, technically, we're taking the square root of both sides, and we really should have a plus and a minus, okay? But I'm only talking about the x's greater than or equal to 0. So my inverse, this is proper notation, f inverse of x, would just be the positive square root of x for x greater than or equal to 0. Okay, so it's just a quick review of how to find an inverse algebraically. You turn it into y equals your function of x, you switch your x and your y, then you solve for y again, and then change the y notation to f inverse of x. Okay, now the next thing I want you to do with that, we're still kind of on number 1 here, I want you to find, so now find the derivative, all right, of the inverse function. Okay. All right. Well, I'm actually going to do it 2 ways. All right. The first way is the obvious. All right. If we start with our inverse function, y equals the square root of x, and I ask you to take the derivative of that, right, with respect to x. So you can either write y prime or dy over dx to show that you're taking the derivative of both sides. So the derivative of the y with respect to x is dy over dx, and the derivative on the other side is a power rule. So we bring the power to the front, subtract the power, and then of course I'll take a second and I will rewrite it. Okay, so that I have positive exponents, and maybe I'll even change it back to a square root. Okay, now I actually want us to do it again. And so we're going to do it a second time, but I want to do it using implicit differentiation. Okay, so instead of starting with y equals x squared, no, excuse me, instead of starting with y equals the square root of x, okay, and using a power rule, all right, I want us to get x by itself. So I'm going to square both sides, and I'm going to take the derivative using implicit differentiation. Okay, I want us to use implicit differentiation. So remember, that means we're finding dy over dx, but we might have to do some work to get there. All right, so I'm going to take the derivative of y squared, but I'm taking it with respect to x, so I need to multiply by that implicit piece, dy over dx, and on the other side I get 1. And so then the derivative, when I get it by itself, is 1 over 2y. Now that doesn't look exactly like the answer I got before, right? 1 over 2 square root of x, but doesn't y equal the square root of x? So then I can use substitution and replace y with the square root of x, and they do in fact equal the same thing. And right now, I know that process seems kind of silly to do it that way, but eventually you're going to need that process. So I'm just kind of practicing. All right, so now I want us to take another derivative. All right, so what if I wanted you to take the derivative of, okay, so take the derivative of y equals the cube root of x, okay? Because that's the inverse of, all right, what function? Hopefully you say x cubed. Okay, well, y equals x cubed. Let me write it as an entire function. Okay? All right, so we're going to do it the old way, right? We're going to take it using a power rule. So the derivative of y with respect to x equals 1/3 x to the negative 2/3. And then I can move that x to the bottom. And you do not have to change it to a radical, okay? All right, but I also want us to do it with this new implicit differentiation way, okay? So, all right, let's go back to y equals the cube root of x, but instead of solving for y, let's solve for x. So I'm just going to cube both sides, and then I'm going to take the derivative, okay? And that's the piece that requires implicit differentiation. So I've got a power rule, but we're taking the derivative with respect to x, so we need our implicit piece, equals 1. Solve for dy over dx. Well, that doesn't look anything like, I mean, I guess there's a few similarities between the answer we got the regular way and the answer we just got the new way. All right, but, right, keep in mind that we know that y is equal to the cube root of x. So y squared would be equal to the cube root of x squared, all right, which is the same thing as x to the 2/3. All right, so it is in fact, even though it doesn't look like it right away, it is in fact equal to the same function. Okay? All right, I want us to do it one more time with one other function. All right, let's say if f of x equals e to the x, all right, then let's refresh our memory on the inverse. All right, again, I'm just practicing different notations. F inverse of x, hopefully you remember the inverse of e to the x is the natural log of x. Okay, so if and now I want you to differentiate f inverse of x. I'm asking you to take the derivative of the inverse. Okay, and again, we're going to do it two ways. I'm going to start by writing it as a y equals problem, and then taking the derivative, of both sides with respect to x, and that one's done. Okay, that was easy. All right, but I also want to show you that it's not the only way to do it. All right, so what if I wanted to start out with x equals? Well, how do you get rid of the natural log? Well, you make it a power of e. So what I'm saying is you make both sides powers of e. Well, this side's going to stay e to the y, but e and ln cancel out to give you x. And now if I start out with that, I can take the derivative of both sides, but I'm going to need implicit differentiation when I take the derivative of the left. So the derivative of e to something, remember, is e to that something times the derivative of that something. And then we get 1 on the other side. dy over dx is now equal to 1, over e to the y. Sorry. All right, but we know that e to the y is equal to x, and so I can substitute that back in, and I do in fact get the same derivative. And again, I know it seems silly to do it the long way, but I have a purpose, okay? In those particular scenarios, using implicit differentiation is not necessarily, right, the most ideal and efficient way to get the derivative, all right? But what if I ask you to find the derivative of y equals sine inverse of x? Okay, so that's an inverse of a trig function. All right, and so that's where I'm going to stop the first video and pick back up with the second video.